Very good morning to all of you. Today we will see in concrete technology the lecture number 21, properties of hardened concrete. At the end of the lecture, you are able to understand the shrinkage, types of shrinkage and their effect. And also you will learn about the elastic modulus of concrete, which is very necessary for design of reinforcement cement concrete. So first we will start with the shrinkage. Uh, there are different types of shrinkages occurs while your concrete is uh, hardened from fresh state to hardened state. So that shrinkages are nothing but the reduction of water from the concrete volume due to uh, removal of your water from the capillary pores. Number of types of shrinkages can occur in concrete, such as plastic, thermal, and sometimes it is called as chemical shrinkage, autogenous shrinkage, drying shrinkage, and carbonation shrinkages. The total shrinkages of concrete depends upon the constituents materials, aggregate, cement paste, water, and size of the member, also the environmental conditions. Because in a hot weather condition, the evaporation losses are more as compared to cold weather concreting. In appropriate circumstances, the maximum limit of cement content in the concrete may also have to be specified, because concrete mixes having high cement content may give rise to higher shrinkage, cracking, and creep in concrete, and also increase the cement paste content. The increase of cement paste content means there is more paste available, and the shrinkage are generally due to the paste. Shrinkages not occurs in aggregates. That's why the paste and property of paste, that is water and cement, they influence more on shrinkages. If you compare with creep, shrinkage and creep are not independent phenomena. For convenience, their effects are treated as a separate and independent. Shrinkage is the reduction of volume of concrete, and the number of types of shrinkage can occur in concrete. That may be the plastic shrinkage, chemical shrinkage, drying shrinkage, and the carbonation shrinkages. The relative magnitudes of the different types of shrinkages are presented in the next slide. You can see here the different types of shrinkages in this figure. As the days or hours pass, or based on the duration, the shrinkages are classified as shown in this figure. You can see the first one is the plastic shrinkage, and all the shrinkages are occur when there are restraints to the volumetric constraint, and that is due to the construction of the paste. Cracking occurs in the concrete. There are various sources of restraint in concrete structures. First, they are restraint due to the aggregate, because when there is shrinkage into the paste, the aggregate restrict the shrinkages, and that leads to the uh, cracking. Therefore, the strain due to the reinforcing bars also in RCC as reinforcement concrete, and restraints are also uh, in a base or a pavement for the road construction and for the airfield or in the industrial flooring. Restraint due to differential shrinkages within the concrete member. Inner side of finger are not exposed to the environmental condition as the exterior surface. Restraint due to the differential shrinkage between concrete members also. There are many restraint, and that leads to the different changes or cracking or surface cracks on the uh, is, uh, uh, concrete surfaces are observed. There are five types of shrinkages as you are seeing in the figure. They are plastic shrinkage, thermal or chemical shrinkage, autogenous shrinkage, drying shrinkage, and the carbonation shrinkage. We will see one by one uh, these different types of shrinkages. The plastic shrinkage, this type of shrinkage is associated with the drying when the concrete is in a plastic stage. It is controlled by both capillary pressure and the effect of sand particles. The sand particles sometimes reducing the plastic shrinkage due to their ability to arrest cracking, generate large water-filled channels, gaps, or pores at and near the cement paste sand interface, that is interfacial zone. These channels tend to get filled up when fine mineral admixture are used. So mineral admixture also arrest the plastic shrinkages. The plastic shrinkage, first of all, you will understand that it is nothing but the reduction of volume of the concrete. So in plastic shrinkage, it occurs at the earlier ages of your concrete production when it is start hardening. Then the reduction rate of evaporation of water, we can control the plastic shrinkage, or by decreasing the temperature of the concrete, placing the concrete at the earliest as we made concrete as soon as we made produce the concrete, and the placing should start at the earliest. Evaporation rate should not exceed 1 kg per meter square per hour. That also, if your evaporation rate is less, we can control the volume stability of your paste, and we will avoid the shrinkage some percentage. Reduction of cement content by optimizing the paste volume using complementary cementitious material that will reduce the shrinkage. Also, the use of non-metallic fibers, carbon fibers, polypropylene fibers, etc., that also reduce the shrinkages into the concrete. Then the second type is the shrinkage due to the thermal or chemical changes due to the hydration of your cement. The overall volume of product formed in cement hydration is smaller than that volume of the reactants, because the volume of the reactants are large and the volume of the end product, the hardened concrete, is less. Thus, there is a shrinkage associated with this chemical reaction. Chemical reaction, it is nothing but the hydration of your cement particles, which is thus called chemical shrinkage. An example of this volume contraction is given already in the chapter of the cement chemistry, or the chapter number 1, as we have seen, and chapter number 2, the production of concrete. The remainder of the volume goes toward the porosity of the cement paste. So because the hydration process or the reaction between the water and the cement paste is nothing but exothermic reaction, the heat is produced and the water will evaporate through the capillary pores or interfacial zone between the paste and the aggregate. Then we'll see the third type of your shrinkage is nothing but the autogenous shrinkage. This is the shrinkage associated with the withdrawal of water from the capillary and the gel pores for the hydration of unhydrated cement. This phenomena is also called as self desiccation. Typical value of 40 into 106 at 1 month, 100 by 106 at 5 years have been reported by researchers. And the factors that affect autogenous shrinkages: fineness of cement, degree and quality of mineral admixture, and the tricalcium aluminate content in the cement. The shrinkage is especially severe at the low water to cement ratio, because the great degree of unhydrated cement is present when the water content is less and unhydrated cement particles are available into the concrete mass. A value of 700 to 106 was reported for a water to cement ratio of 0.17, very less water to cement ratio. And for the normal concrete, the strain, or you can say the deformation, are much smaller than drying shrinkage strains. है ना? So autogenous shrinkages are normally due to the fineness of cement and also the tricalcium aluminate content of your cement. We see the fourth type of shrinkage, that is the drying shrinkage, is often referred as the simple as a shrinkage. These drying shrinkages are large and is caused by the evaporation of water from the concrete. The creep and shrinkage both are the evaporation of water from the concrete, but creep is the forcible evaporation of water from the concrete due to sustained loading. But shrinkage is evaporation of water during the production or after the production of your concrete, and many changes in volume are occur at the time of drying shrinkages. Said Raza, what is the time now? The drying shrinkage, this is the shrinkage associated with the removal of water from concrete by drying. Only the cement paste in concrete is susceptible to drying shrinkage. Numerous factors affecting drying shrinkages, such as the climatic condition, or you can say the ambient conditions during the production and curing of your concrete, water to cement ratio, and size of your specimen, amount of aggregate, and degree of hydration. Because aggregates are given are providing a stability to the concrete, and the change in volume of aggregate is negligible, almost nil. The changes in the volume of for during the process of hardening of your concrete is only in the paste, and that is termed as shrinkage. Then the last, but not the least, the shrinkages due to the carbon reaction, and that is called as the carbonation of your concrete or carbonation shrinkages. This type of shrinkage is not associated with the loss of water or any other loss of material from the concrete. In fact, carbonation or the attack of concrete by atmospheric carbon dioxide, the carbon dioxide causes an increase in the mass by reacting the calcium hydroxide. The reaction of carbonation can be written as follows. You can see here the reaction, the CaO2, that is carbon hydroxide, it reacts with the carbon dioxide into the atmosphere, and the calcium carbonate is produced. And the calcium carbonate is produced, and water is released. So this water is released, you can see, and you see the stage wise reaction. Then in the first stage, second stage, and third stage, the calcium hydroxide Ca2 plus ion plus 2 OH minus ions. The 2 OH minus ion react with the carbon dioxide, produce the calcium carbonate, and the water is released. So this carbon calcium carbonate is formed, and the water is released, and that is harmful for the concrete. So you understand that shrinkage is nothing but the reduction in the volume of your concrete. In the second part of today's lecture, lecture number 21, we can see the elastic modulus, or the modulus of elasticity of concrete. Generally, the modulus of elasticity is needed for the design purpose. The concrete is not an elastic material, and you know very well this, because the elastic materials, they will retain or regain their original shape after removal of your loading. In addition, it is non-linear and exhibits a linear resistance curve, and the elastic constants such as model of elasticity and Poisson ratio are not strictly applicable for the concrete. However, they are used in the analysis and design of concrete structures, assuming elastic behavior. So thus, the modulus of elasticity of concrete is a key factor for estimating the deformation of building elements, as well as a fundamental factor for determining the modular ratio M used for the design of your reinforced cement concrete. The use of high strength concrete will result in a higher modulus of elasticity and in reduced deflection and increase the tensile strength. The modulus of elasticity is primarily influenced by the elastic properties of the aggregate and to a lesser extent by curing conditions, mixed proportioning, porosity of concrete, and type of cement. It is normally related to the compressive strength of concrete and may be determined by means of extensometer attached to the compression test specimen as described in the IS 516 1959. Please unmute your mic. Someone is disturbing the class, please. The elastic modulus is also called as the modulus, Young's modulus of elasticity, and it is a ratio of axial stress to the axial strain within the elastic range. That is the Young's modulus of elasticity. When the loading is of low intensity and for short duration, the initial portion of stress and curve of concrete, its compression is linear, justifying the use of modulus of elasticity. However, when there is sustained load, an inelastic creep occurs even at relatively low stresses, making the stress-strain curve non-linear. Moreover, the effect of creep and shrinkage will make the concrete behave in non-linear manner. Hence, the initial tangent modulus is considered to be measure of dynamic modulus of elasticity by Neville and Brooks in 2010. When linear elastic modulus analysis is used, one should use the static modulus of elasticity. For that, various definitions of elasticity are available. It may be initial tangent modulus. You will see in the figure all this modulus, tangent modulus at the specified stress level, and the secant modulus is also at the specified stress level as seen in the figure below. You can see here the stress strain curve of your concrete. The ultimate stress will be there, and strain is also increasing after the unloading, but stress is reducing. And you can see the tangent modulus by this curve at the specified stress level. And this is the unloading curve, you can see here. Okay, and the initial tangent modulus start from the origin of this curve, and you can see this line, straight line, that is the uh, secant modulus, and this therefore the different modulus of elasticity or various modulus of elasticity can be defined using this stress strain curve of your concrete. The secant modulus, which is the slope of line drawn from origin to the point of stress strain curve, corresponding the 40% of failure stresses, corresponding to the 40% of failure stress, and is found to represent the average value of EC, that is the modulus of elasticity, under service load conditions, under service loads or under working load conditions only. Is also given by the Neville and Brooks. And as per our Indian Standard Code, that is IS 456, it suggests that the short-term static modulus of elasticity of concrete EC is equal to 5000 under root of FCK Newton per mm square, because FCK is the characteristic strength of your concrete at 28 days. So this is the relationship also between the elastic modulus to the compressive strength of your concrete. This figure already we have discussed. Then you can see the elastic modulus of elasticity is primarily it is influenced by the elastic properties of aggregate, and to a lesser extent by the condition of curing, age of concrete, the mixed proportions, and the type of cement. The modulus of elasticity is normally related to the compressive strength of your concrete. That relation you have seen already. EC is equal to 5000 under root of FCK Newton per mm square, where EC is the short-term static modulus of elasticity in Newton per mm square, and actual measured values of this elastic modulus will differ by plus minus 20%, plus minus 20% from the values obtained from above expression. So today we learn in hardened properties of concrete two things. First one is the shrinkages into the concrete, and second one is the modulus of elasticity of your concrete. So these two properties of hardened concrete are very important and regularly asked in the examination. So this is the properties of hardened concrete. And shrinkage, you can see the different types of shrinkages also we have seen today, and we have also discussed about the types of shrinkages and how to control these shrinkages. So we will stop here, and if any doubt in your mind you can ask with me about the shrinkages of your concrete and the elastic modulus of your concrete or modulus of elasticity of your concrete. So in a third year diploma student, they also use the modular ratio while designing the beams in reinforced cement concrete design. So if any doubt or any question you may ask, otherwise we will end the lecture. Thank you for joining. Very less attendance in the first lecture